This is question 15.5.51. It states that there is a realty group that would like to develop a regression model to help the firm set weekly rental rates for beach properties during the summer season. So independent variables for this model will be the size of the property in square feet, the number of bedrooms and bathrooms it has, and its age. So it sounds like we've got 4 independent variables. The data is included in this table here. So I'm going to go ahead and copy to the clipboard. And let's place it into an Excel sheet here. Okay, so rental rate, that's our dependent variable, and then we have 4 independent variables here. And part A says that we want to use a software package like phstat. So remember, for this course we are using Excel stat instead of phstat. But we first want to check for multilinearity. So with this, with multilinearity, we can utilize the data analysis toolpack and just run a number of regressions to find the R-square for each scenario, and then run that through the multilinearity equation or formula, which is 1 over 1 minus R squared. So that would take some work to do. Basically, what we have to do to check, to get the VIF, is run a regression with each of these independent variables taking turns as the dependent variable, with the other 3 being the independent variable. So we basically forget about the dependent variable for now in the problem. We start with bedrooms, we make that the dependent variable, we make the other 3 independent variables. We get the R squared for that regression, we plug that into the formula, 1 over 1 minus R squared. That gives us our VIF. Then we do it for age. We have age be the dependent variable, and then we have bedrooms, bathrooms, and square feet be the independent variables. Run the regression, get the R squared. Plug it into the formula, 1 minus 1 over R squared. So we have to do that for every single one. So we'd have 4 different regressions to run. So instead of doing that, obviously we can just get the information much more quickly by running it through Excel stat. So let's do that real quick. We just need to plug in our dependent and independent variables. And when we start out a question like this, the lab doesn't give us access to all the different questions right up front. So at this point, all we would usually see is part A. All we know is we need the VIFs. So we wouldn't know what type of regression it eventually wants us to run or what the alpha is. So really at this point, we would just run a basic regression, and we need to make sure that we have the levels correct, which is 4 independent variables. The confidence interval is already set at 90. I'll just leave it there for now. And have a stepwise regression set up. I don't even need to do that. We'll just do a basic regression, straightforward regression, again, just to get the VIFs. Go to outputs, and we have the multilinearity statistics. Really, we wouldn't even need to select the analysis of variance, but we'll go ahead and just leave it as is. And let's check for those figures now. Select again all the independent variables. And as you can see here, we have the VIFs for each independent variable. Okay, so those look correct from what I had pre-filled in here. So 7.2, 1.1, 1.7, and 6.3. So now we have, just from looking at this, we have 2 VIFs that are over 5 and could be a concern. So we use in this textbook 5 as a rule of thumb. So a VIF of over 5, kind of consider that to be our hurdle. Anything greater than 5 being somewhat unacceptable. Like I've said in other videos, that number in some research can be as high as 10, and still doesn't mean that if you had a VIF over even 10 that it wouldn't necessarily be okay to have it in the model. But just to try to keep things more black and white for the course, we're just going to operate with the notion that anything over 5 is not acceptable and needs to be dealt with. Notice before we go on that there is something here within the multilinearity statistics called tolerance. The tolerance statistic is also another measure of multilinearity, and with this, it's really just the inverse of the VIF. So to calculate the tolerance, if we had the VIF for bedrooms, which we do, then all we would need to do is take 1 divided by that VIF figure, and that gives us our tolerance score. So a tolerance, typically anything below 0.2 would be our concern if we're utilizing a VIF hurdle of 5. So again, that's just 1 divided by 5, which is 0.2, and that's what lets us know what our hurdle is for the tolerance if that's what we were making our determination from. Okay, so with that in mind, question B asks us to take the necessary step of either removing one or more independent variables if we feel it's needed. So this is a little bit of a, I don't want to say trick question, but it does make you consider, what do we need to do when there is a more than one variable that has some multi-collinearity. So the rule of thumb is that we don't just immediately throw out anything that is over 5. What we do is we take out or we remove the highest VIF score, in this case bedrooms, and we rerun the regression. So we'll find out that if we rerun the regression, a lot of times the other offending variable will fall back in line. So in this case, we're only going to remove bedrooms at this point, and then we would rerun the regression. And we can do that as well, just to test it. If we were going to remove bedrooms, let's just see what that looks like. And we'll see it in other regressions as well, but let's just remove bedrooms and we'll do age, bathrooms, and square feet. And now we can see that now age, bathrooms, and square feet of the 3 remaining variables are all below 5, well below 5. So square feet was 6.3, we removed the higher VIF, and that got the square feet variable back in line. So that's why we wouldn't just immediately toss out both to begin with. Part C does want us to perform a best subsets regression. And so let's take a look at best subsets. Just going to go back into the box here. And we've already set the independent variables to remove bedrooms, so nothing that we need to really change there. This is going to include age, bathrooms, and square feet. And we are going to select the model of, this case, it's Excel stat called a best model. This is commonly referred to as best subsets. And we're going to base the best subsets on the adjusted R squared, kind of the most common, as opposed to an error term. And minimum variables, we do need to have something in here. So minimum variables, we need to have, of course, return at least 1 variable for the model. The max variables, I'm going to set that at 3 because at this point we have 3 independent variables. So it's possible that obviously we could have all 3 be the best model. And let's check outputs. We have some residual statistics there we can look at. Analysis of variance, multilinearity statistics. I'll go ahead and keep that in there. And let's just take a look and see what we have. So as you can see, this is the 3rd regression that I ran just very quickly. They're just stacking up down here on the bottom. I can delete any of these regressions at any point in time if I don't want them, or as I'm updating them as I go. All right, so these are the results. We've got the things we looked at here, the multilinearity statistics, and this is the applicable regression table here. So what this is telling us is that it first ran the regression with looked at a few different options. One with just bathrooms. We have a regression with bathrooms and square feet, and then we have a regression with age, bathrooms, and square feet. So all 3 independent variables that were left over. So if we look at the adjusted R squared, this is what we want to base our decision on. And this kind of introduces a little bit of a gray area in statistics, or in model building, I should say more specifically. So this is kind of a gray area of model building. And what we're looking at here is strictly by adjusted R-square, we would accept the best model as being one that includes all three of the remaining independent variables, age, bathrooms, and square feet. However, as a rule of thumb, if we look at adding a variable, in this case, it's age, because age was added between the second and the third different runs here. Age is the difference. If we look at adding a variable and it does not do really much of anything to the adjusted R squared, there's no sense in keeping that variable. So the rule of thumb is you want the highest adjusted R squared with the lowest number of variables. So although our regression results would point to us keeping all three of these independent variables, we really would not want to include age. And once again, because there's very little difference in the adjusted R squared, we're looking at just 5/1000ths of a difference. So really our best model in this case is not the third one here, but it's actually going to be just the bathrooms and square feet, which is x sub 3 and x sub 4 in our data. So this is x sub 3, this is x sub 4, bathrooms and square feet. Okay, and for part D, we are identifying the regression equation. So here's where we are going down and inputting our coefficients, but notice that the coefficients for this model are based on all three of the independent variables. So if we're really just going to use a model that has bathrooms and square feet, we need to rerun this again and get rid of age as a variable. So here we need to go back and rerun the regression another time. So this question is definitely a fun one for kind of getting into the weeds with model building. So I'm going to change the independent variables to just x sub 3 and x sub 4, which is bathrooms and square feet. And I ran this as a best subsets as opposed to just a regular regression. Really didn't need to be a best subsets regression. I didn't change the type of regression I ran. I could just run a basic regression, but I still get the same coefficients either way. It's still going to run, instead of just running those two independent variables, you see the options here is looking at bathrooms by itself and bathrooms and square feet together. So once again, didn't need to run it as a best subsets. Could just run it as a straight regression. Just only avoided a couple of clicks. But these are now the updated coefficients for the new, or I guess you could say final model. We have our independent variable. We have our slope for the bathroom and our coefficient slope for the square footage. Okay. And then for the last part, part E, we are to perform a residual analysis with the model in part C to determine if the conditions for the model are met. And typically here, there are a few different conditions for residuals, but a lot of what we're looking for here is constant variance or homoscedasticity. So here's a little bit of a deficiency with Excel stat is that the residuals, it will give you the residuals, which is the difference between the actual observation of the dependent variable and the predicted observation for each dependent variable. But as far as the residual plots go, it really just plots the dependent variable as opposed to the independent variables. And so what we're looking for with homoscedasticity is the residual plots of the independent variables. So here's a case where we want to actually go back and just run it really quick through the data analysis toolpack to look at the residuals. So I'm going to go back, and here I go running another regression, this time through the data analysis toolpack. I'm going to go data analysis, and set this is off a little bit. independent variables. But definitely some good practice here for this particular problem. We've got the output range. I'll just stick that right here, top. And so see, I've got residuals checked, and I have residual plots. Now the residuals are included in the Excel stat output, so I don't have to do it here, but I'll just leave it checked. Let's go ahead and hit OK. And here we go. So should be no surprise that our output shows the correct coefficients for the problem, and all the other statistics will be the same as far as F stat. Very high F stat here, very, very low p-value. I see that negative 14 there. That's basically saying that there's 14 preceding zeros before these numerals. So this is way, way, way below 0.001, so it's close to 0.000. So a statistically significant model. And you can see our p-values for the independent variables are all very good. So all this one here is a little above 0.001, but still very, very low, well below 1%. And same thing with this p-value, very, very low, well below 0.00 or 0.01 as well. So these are significant variables. And again, the main point though of running this regression was to get the residual plots. And so we look here, these are the residual plots of the independent variables, square feet and bathroom. And as I've said before, oftentimes you look at these plots and it's really hard to tell, is there heteroscedasticity here or not? This one here is, I guess, for most researchers or most people that looked at a lot of these, this one is a lot more obvious than maybe what you would see in other examples. Again, there's not very many independent variables, only 2. So with more independent variables, more observations, more bigger sample, this could be more difficult to try and find a pattern. So, but what we're looking at is like this little bubble here in the middle on the bathrooms, and kind of this little gathering here. It looks like there's a little bit of a pattern starting to form. This is a bit concerning. So in advanced statistical applications software, we would run a correction for this issue here. But bottom line, just for our question, our purposes, it does look like both independent variables do show some pattern, and so that constant variance assumption is not met really for each variable. So this isn't necessarily a deal breaker for the model, but like I said, with more advanced statistical software, SPSS or eViews or Minitab, those sorts of things, we'd need to run some corrections, and that would change our model a bit as well. So it's possible that we run a correction and it throws one of the p-values for one of our variables off and knocks down the f-stat for the model. So it could essentially, with a correction, it could make this a less appealing model, or maybe even throw out or make insignificant one of the independent variables as well. So that's how we work through this question. Again, this gets us deeper into model building, and with real-world research and problems, it does get a bit deeper than this, but this is certainly some good example and some good practice for how to put a model together.